Hello everyone, in this video we ABAQUS with explicit method. The objective is to have a good idea why we use this type of explicit analysis of many dynamic problem compared to standard method, and to estimate time of stability use as a principal properties of dynamic analysis. Please, if you have any question or request, contact me in my Facebook page and my email. What is explicit dynamics? The dynamic for convenience with the inertial forces isolated from the other forces using following formula, where P is the external load vector and I is the internal load vector and I is the internal load vector. These equilibrium equations are completely general. They apply to the behavior of any mechanical system and contain all nonlinearities, large deformations, nonlinear material or response, contact. When the first term, the inertial or dynamic force, is small enough, the equations reduce to the static form of equilibrium. Explicit dynamics is a mathematics of motion through. The explicit dynamic integration method is also known as the forward-Euler or central difference algorithm. Central difference algorithm. Unknown values are obtained from information already known. Combining the explicit dynamic integration rule with elements that use a lumped mass matrix is what makes an explicit finite element program work. The lumped mass matrix, M, allows the program to calculate the nodal accelerations easily at any given time, t, using the following expression. In this expression we can conclude that acceleration it depend to matrice Stiefenier and difference between internal and external load. ABAQUS Standard and ABAQUS X with two complementary analysis tools. ABAQUS Standard provides the capability to analyze the following types of problems: linear and nonlinear static and linear dynamic. Low speed, low frequency response, nonlinear dynamic. Nonlinear heat transfer. Coupled temperature displacement, quasi-static. Coupled thermal electrical. Mass diffusion problems, structural acoustics. ABAQUS Explicit provides the capes of problems, high-speed, short-duration, dynamics used in drop tests and crash analyses of structural members. Large, nonlinear quasi-static analyses used in deep drawing, blow molding, and assembly simulations. Highly discontinuous, post-buckling and collapse simulations. Coupled temperature displacement, dynamic, discussed in the heat transfer and thermal stress analysis with ABAQUS. And structural acoustics, discussed in the structural acoustic analysis with ABAQUS. What is the advantages of ABAQUS equilibrium, P-I equals 0, in structural simulations? It provides a large number of element types for modeling many different types of problems. It provides analysis capabilities for studying a wide variety of non-structural problems. It uses a very robust and proven contact algorithm. It uses an integration method for transient problems that has no mathematical limit, stability limit, on the size of the time increment. The time increment size is limited only by the desired accuracy of the solution. What is the advantages of ABAQUS discontinuous, high-speed dynamic problems efficiently? It has a very robust contact algorithm that does not add additional degrees of freedom to the model. It does not require as much disk space as ABAQUS Standard for large problems, and it often provides a more efficient solution for very large problems. It contains many capabilities that make it easy to simulate quasi-static problems. Why use ABAQUS, explicit, address. ABAQUS, explicit contains many modeling capabilities that do not exist in ABAQUS standard, for example, material standard, for example, material failure with element deletion for elastic plastic materials. It can simulate larger models more readily with a given amount of computer hardware. It is easy to learn. The basic input structure and options for an ABAQUS, explicit model are the same as those for an ABAQUS, standard model. It is economical to add ABAQUS, explicit to your network. The network licensing system allows a site to get both analysis programs at an attractive cost. Some challenging problems, we motivate explicit by briefly reviewing some complicated problems suitable for analysis with ABAQUS, explicit. Some applications we can see for example, rubber door seal, wire crimping, gas tank impact, column buckling, metal forming, wiper blade. In following picture we illustrate the many uses of explicit dynamic analysis applications. In this last part we will see stable procedure solves every problem as a wave propagation problem. Out-of-balance forces are propagated as stress waves between neighboring elements. A bounded solution is obtained only when the time increment t is less than the stable time increment tmin. If increment t is greater than or equal to increment tmin, the solution will be unstable and oscillations will occur in the model's response. The stability limit can be defined in terms of the highest eigenvalue in the model, omega max, and the fraction of critical damping, Xi, in the highest mode. The condition is illustrated in bellow and we can see also thus, damping reduces the stable time increment. The concept of a stable time increment a one-dimensional problem. The stable time increment is the minimum time that a dilatational, i.e., pressure wave takes to move across any element in the model. Dilatation consists of volume expansion and contraction. The dilatational wave speed, C elastic material, with Poisson's ratio equal to 0, has bellow. E is the Young's modulus and ρ is the current material density. Based on the current geometry each element in the model has a characteristic length, Le. For shells and membranes the stability limit is based on the mid-plane or membrane dimensions only, for beams it is based on the axial dimensions. When the transverse shear stiffness is defined directly for shell elements, the stable time increment will also consider the transverse shear behavior. Thus, the stable time increment can be Le and or increasing CD will reduce the size of the stable time increment. Decreasing element dimensions reduces Le. Increasing material stiffness increases CD. Decreasing material compressibility increases CD. Decreasing material density increases CD. Thank you for your attention. If you have any, contact me in my email and my Facebook page. Wish you also all good news and stay safe.